For years, we've mostly talked about AI solving very specific things, right? Like recognizing a cat or beating a human at Go or chess. But now it feels like we've hit this really fascinating new stage. The AI isn't just spitting out answers anymore. It's actually learning how to do the math discovery itself, like the methodology behind it. It's kind of optimizing the whole optimization process, if that makes sense. So today we're going to really dig into AlphaEvolve. It's this groundbreaking system. And what it does is it combines, well, the brute force of evolutionary search with the smarts of large language models, LLMs. And it uses this combo to propose, test, refine, create these really complex algorithms for some super tricky math problems.
Exactly. And this deep dive is really about figuring out how they manage that, because AlphaEvolve kind of has two main ways of operating, two core philosophies, you could say. There's the search mode, think practical, results focused, and then there's the generalizer mode, which is way more ambitious. Getting the difference between these two.
Well, that's crucial, really. It shows two different ways of thinking about mathematical breakthroughs.
And the results they talk about in the sources, they're pretty stunning. We're talking about AlphaEvolve just autonomously discovering new mathematical constructions, things we didn't know before. And often, these are matching or even improving on the best solutions humans had found in areas like combinatorics or number theory.
And fast.
Right.
Yeah.
It apparently only needs hours of prep time. It's like it's seriously speeding up how we do constructive mathematics. Okay, let's unpack that then, starting with this search mode, which you said is kind of the default.
That's right. So let's say a mathematician just needs the best possible answer for one specific setup, like, I don't know, the absolute best way to pack exactly 11 spheres. Why does AlphaEvolve go about it in this sort of unique two-step fashion?
Well, the search mode, it's laser focused. It's purely about optimization. It honestly doesn't really care if the solution is elegant or makes sense as a general rule.
Right.
Its only goal is finding the very best numerical result for that specific problem instance, full stop. And the key mechanism here, and this is maybe the most surprising thing from the research, is that AlphaEvolve doesn't directly evolve the final answer, the construction itself.
Oh.
No. Instead, it uses the large language model, the LLM, to evolve a program. And this program acts as a search heuristic.
Wait, hang on a sec. So you're saying the LLM, the big brain AI, isn't actually writing the final math thing?
Correct.
It's writing like a specialized piece of software,
Yeah.
an algorithm.
Yeah, a search heuristic.
And that thing then goes off and searches for the best actual object. Why the extra step? Why the middleman? Wouldn't it be simpler, or isn't the LLM smart enough to just find the answer directly?
Ah, well, that's where the cleverness about speed and scale comes in. See, making a call to one of these really powerful LLMs, it's actually quite slow, computationally speaking, and relatively expensive.
Okay.
But that one slow, expensive call can generate this highly specialized, fast search tool, the heuristic. And then that heuristic, it gets a fixed, pretty short time budget, maybe, say, 100 seconds. But in that short time, because it's cheap to run, it can trigger these massive computations. It can explore millions, literally millions, of possible constructions in parallel.
Ah, okay, I get the optimization now. So you use the expensive, slow intelligence the LLM just wants to design the perfect little tool, and then you unleash that cheap, fast tool and let it run millions of times using cheap computing power.
Exactly.
That really is like a meta-level optimization, optimizing the search itself.
Precisely. They're optimizing the search strategy. And what's cool is that this leads to something they call emergent specialization. Kind of mirrors how humans think, actually.
How so?
Well, the early versions of the heuristic that the system evolves, they tend to perform these broad exploratory searches. Just trying to get into the right general area, the right ballpark.
Okay.
But as the system keeps refining the heuristic program, later versions emerge that are much more specialized. They focus on fine-tuning, making tiny, clever improvements when they're already close to the best solution. It's like they evolve from being a map maker, a cartographer, to being a highly skilled surgeon.
That surgical precision. Yeah, that sounds ideal for these really tough, specific problems. Can you give us an example where this search mode, this optimization specialist really shone?
Sure. A great example from the paper is the arithmetic Kakeya problem. It's a notoriously difficult problem in combinatorics. It's about constructing these large sets that have certain restricted arithmetic properties. It's tricky stuff.
Right.
So AlphaEvolve used its search mode specifically to find the best possible constructions for certain fixed parameters, like specific sets of slopes in the problem. And the final construction it found through this totally automated search Well, it turned out to be so insightful, so novel, and well-optimized
Yeah.
that it actually inspired a whole separate new paper by one of the authors who worked on AlphaEvolve.
Wow.
So even though the process, the evolved heuristic itself might be a bit of a black box, hard to interpret,
Mm-hmm.
the final object it finds, the actual mathematical construction, is still tangible, analyzable, and clearly valuable.
Okay, so that's the search mode, the optimization powerhouse. But like you said, finding the best answer for N11 doesn't necessarily tell you the rule for all N11. It just doesn't give you those universal laws.
Exactly. Optimization isn't generalization.
Right. So if you're actually looking for a formula or a construction method that works for, say, any number or any prime number,
Hmm.
you need something else entirely. And that, I assume, is where this generalizer mode comes in. This sounds much more like traditional theoretical math aiming for the big picture.
It is. It's definitely more challenging. And interestingly, it often demands a kind of elegance, not just brute force. The generalizer mode's whole job is to evolve programs that produce these general constructions or maybe even actual closed-form formulas. The key is that these have to be valid for any input value within a certain class, like, all integers, null or dollar,
Yeah.
or perhaps an infinite set of primes, ball or dollars. And to make that happen, the way it's evaluated has to change quite dramatically from the search mode.
How so?
Instead of just checking one fixed case, AlphaEvolve tests the candidate program on many different input values, and often very large ones. Think large primes or tall seam numbers, way bigger than you'd ever check by hand.
Okay, stress testing it.
Exactly. And the program's final score isn't just based on one result, but on its average performance, like the average normalized size of the construction it produces, across all these different large inputs.
Okay, so you're demanding robustness by throwing complexity and scale at it. Makes sense. But isn't there a danger there? Couldn't it just learn to handle those specific large inputs really well, kind of overfitting to them, without finding a truly general, elegant solution? Why does testing on huge numbers necessarily lead to elegance rather than just, bulletproofing against weird edge cases?
That's a really critical question. And the answer they found is, well, it's quite counterintuitive again. It turns out that generalization, finding that elegant core idea, often actually improves when the system is deliberately constrained, when it's given access to less data, not more.
Less data. How does that work?
Yeah, it's like a cognitive trick they play on the AI. So when they were specifically looking for an interpretable program, a general formula, the researchers sometimes constrained AlphaEvolve. They'd only show it the best-known solutions for, say, small values of dollars. Just a few examples. Think of it like Sherlock Holmes. If you flood him with 500 tiny, confusing clues, he might get lost in the noise.
Yeah, analysis paralysis.
But if you give him only the 2 or 3 most critical, fundamental pieces of evidence, he's almost forced to come up with the simplest, most elegant theory that explains just those key facts. And that simplicity, that elegance, is often the very essence of generalization.
Okay, I really like that analogy. Starve it of the noisy detail so it has to find the fundamental pattern. Clever. So what's a concrete example where this generalizer mode, maybe using that less is more trick, actually found one of these universal rules or general constructions?
A really good example they discuss is the Nicodim problem. Specifically, it's problem 6.1 in the source material. It's about the size of certain geometric sets, Nicodim sets, in finite fields. A classic, quite open-ended problem.
Okay.
And the researchers here were very clear. They weren't just looking for one good example. They explicitly wanted a construction method that would work for all primes or all prime powers. So naturally, they used the generalizer mode. And AlphaEvolve successfully discovered a really interesting general construction method for it. And just like with the KKI result from the search mode, this general finding was significant enough that it directly inspired a new paper by one of the collaborating authors. So you see, the output from the generalizer mode isn't just meant to be the best number. It's designed to be a springboard for new theoretical understanding.
Okay, so let me try and synthesize this a bit. We've got the search mode, that's the super optimized specialist. It gives you these specific, often record-breaking results for fixed problems, like building the perfect bridge for one specific river crossing.
Right. The best possible answer for that case.
And then you have the generalizer mode, which is aiming higher. It wants the universal, elegant formulas, the things that lead to fundamental understanding. More like discovering the law of gravity that explains why all bridges need certain structures.
That's a great way to put it. The distinction is really crucial. It is. And what's really exciting is that when AlphaEvolve does succeed in that generalizer mode, finding one of those elegant general rules, it can kick off this much larger, almost fully automated AI research pipeline they've built.
Oh, interesting. How does that work?
Well, For example, remember we talked about the Kaikeya problem.
Right.
When AlphaEvolve, in generalizer mode this time, found an interesting general construction for the finite field version of Kaikeya,
Yeah.
they took that programmatic solution, the code it generated, and automatically fed it straight into another system called Deep Think.
Deep Think. Okay, another component in their pipeline. What's Deep Think's job? What does it do once it gets this program from AlphaEvolve?
So Deep Think is essentially an AI mathematician focused on proofs. Its job is proof generation. And in this Kaikeya example, it took AlphaEvolve's program and successfully derived a formal mathematical proof showing the construction was correct. Wow. And it even worked out a closed form formula. Yeah. A nice, neat equation that humans can read for the size of the construction. And then, to really nail it down, that proof generated by Deep Think was then formally verified using something called the Lean Proof Assistant, which involved yet another tool, AlphaProof.
Okay, hold on there. Lean Proof Assistant. For listeners who might not be familiar, what exactly is that?
Right. Think of Lean as hyper-rigorous mathematical checking software. It verifies every single step of a mathematical proof with absolute formal logic. It's designed to catch any tiny human errors, any implicit assumptions, any leaps in logic. If Lean says a proof is okay, it is really okay.
Got it. Like ultimate peer review by computer.
Pretty much. And this whole workflow they demonstrated, discovery using AlphaEvolve's generalizer mode, then proof generation by Deep Think, then formal verification in Lean via AlphaProof, this whole chain.
Yeah.
It really shows the potential for a highly automated, maybe even eventually fully automated, pipeline for mathematical discovery and verification, reducing the time from a new idea to a rigorously checked truth down to potentially just hours.
That really is astonishing. The speed potential there is incredible. But, amidst all this talk of automation, the papers also seem to highlight one factor that keeps popping up as crucial, the human element, right?
Oh, absolutely. That comes through loud and clear. The system's performance, how effective it is, seems very much tied to the quality of the advice or the initial setup given in the prompt by the human researchers.
So the humans are still guiding it.
Very much so. Especially when human experts suggest insightful things, maybe hinting at a certain type of symmetry to look for or a known constraint in the problem space. That kind of guidance almost always led to significantly better results from AlphaEvolve. It really seems like, at least for now, the magic combination is that human mathematical intuition setting the stage and pointing the way. That combined with AlphaEvolve's, relentless, powerful computational search, that partnership seems to yield the best results overall.
So we've really seen today how AlphaEvolve's flexibility, its ability to switch hats, sometimes being this pure optimization machine in search mode, other times being this seeker of universal laws in generalizer mode, how that allows it to make contributions to math at really different levels of abstraction, from specific answers to general theories.
Definitely. And for me, maybe the most fascinating takeaway, especially from the generalizer mode, is that counterintuitive idea we discussed. The notion that sometimes generalization actually improves when you give the system less data, a more constrained view.
The less is more principle.
Exactly. That having too much raw detail isn't always helpful for finding the big picture. Sometimes simplifying the input, forcing it to connect fewer dots, is what encourages those really fundamental breakthrough ideas to pop out.
Which leaves us with a final thought, maybe a provocative one, for you, the listener, to chew on. If constraining the input data can push mathematical AI towards more universal, more elegant solutions, could that same less is more principle be applied effectively in other complex fields?
Interesting question.
Like, imagine forcing a medical AI to diagnose based on just 3 fundamental biological markers instead of tens of thousands of data points. Could that kind of constraint, maybe paradoxically, lead to simpler, more robust, and ultimately more generalizable breakthroughs in other areas too? Something to think about, that sort of meta-algorithmic puzzle as you go about your week.